morning.
Morning.
I hope you all saw that I posted a study guide for next week's exam on Blackboard. So as I said in my email, or in my announcement I should say, the material relevant for the next exam will comprise anything including citric acid cycle, meaning also the pyruvate dehydrogenase complex, anything that I discussed from that point on until now, so including Tuesday's lecture, everything I'm going to discuss today will be relevant for the third exam. Any questions about this? Okay, so I hope you remember this slide, which I showed early this semester when we talked about general principles of metabolism. And I told you that one can break down the metabolism of a heterotrophic organism pretty much into two parts, catabolism and anabolism. And we so far talked about the degradation of carbohydrates, fats, and proteins for energy production. And we saw that energy carriers in the form of ATP, also NADH and FADH2 are being produced. The latter ones can be utilized to produce ATP, as we just learned recently. And what we are going to focus on in the next few weeks actually is how energy is being utilized in biosynthetic reactions, so in anabolism, to synthesize biomolecules, including more complex biomolecules. So here we just see the reactions or the overview that leads from already relatively complex molecules like amino acids and nitrogenous bases to the corresponding polymers, excuse me. But we will actually also include the discussion of the synthesis of the more simple building blocks before then we talk about how they can be utilized in polymerization reactions. So we're going to talk about anabolism, and we will start with carbohydrate biosynthesis, and here we will focus first on the synthesis of glucose. Glucose can then be utilized for the synthesis of all other sugars, and then we'll take a look at the utilization of carbohydrates, monosaccharides, for polymerization reactions that lead to oligosaccharides and polysaccharides. Okay, we'll just take a look at some examples for each of these categories. So we'll start with the synthesis of glucose. As I said numerous times before, glucose is being synthesized in a process called gluconeogenesis. I have a couple of fun facts, okay, things that I came across over the years, which I find relatively interesting. So gluconeogenesis occurs in all animals, plants, fungi, and microorganisms, which already highlights the importance of glucose as a metabolic fuel. If we look at ourselves, humans, glucose, and I mentioned a couple of things like this before, is a preferred energy source for example, erythrocytes, which can only use glucose, but also the brain, neural tissue, testes, renal, medulla, and embryonic tissues. Doesn't mean that all these tissues can only use glucose, okay? We've heard, for example, that the brain can also utilize ketone bodies, okay, but the preferred fuel for these tissues is actually glucose. So gluconeogenesis in mammals occurs in the liver, but also in the kidney, and I found that the enzymes for gluconeogenesis are also expressed in the intestine and the pancreas. To what extent this really contributes to the overall glucose concentration in our body is quite questionable, I guess. So primary importance here for us is gluconeogenesis as it occurs in the liver. And the liver can use, and the other tissues I suppose, can produce glucose, can utilize a variety of different precursor molecules for the synthesis of glucose. So we will focus our discussion of the utilization of pyruvate, because pyruvate is the molecule that also is produced in the opposing pathway glycolysis, as we've learned But we'll see that the pathway that leads to glucose, if lactate is a precursor, is a little bit different. But then also glycerol and the glucogenic amino acids can be utilized for glucose synthesis. Okay, so as I just said, glycolysis and gluconeogenesis are opposing pathways. Glycolysis, as we've learned, breaks down glucose to 2 molecules of pyruvate, and then under anaerobic conditions, muscle tissue, for example, can be converted to lactate. Okay. But we can also synthesize glucose utilizing molecules like pyruvate or lactate. And I told you previously that glycolysis and gluconeogenesis actually share a number of steps. Okay, so as you remember, glycolysis is composed of 10 enzyme catalyzed reactions, and there were only a couple actually that were irreversible because they were exergonic under physiological conditions. Do you remember which steps these were? 1, 3, 10. So what were 1, 3, 10? Do you know? You're right. But do you know which reactions these were?
It was hexokinase.
The hexokinase reaction, or hexokinase or glucokinase in the liver, yeah?
And then phosphofructokinase 1.
Phosphofructokinase 1, yes?
And then it's pyruvate dehydrogenase.
No. Pyruvate dehydrogenase actually converts pyruvate to acetyl-CoA. Close. Pyruvate kinase. Okay. So these are the 3 enzymes that in glycolysis catalyze irreversible reactions. So as we've learned before, irreversible means irreversible. Okay, so we cannot use these 3 enzymes to catalyze the reverse reactions to utilize these in gluconeogenesis. And for that reason, gluconeogenesis deviates from glycolysis in exactly these 3 reactions, overall conversions of the intermediates, the corresponding intermediates into the resulting intermediates, let's say. Don't want to say products here. So what this requires then in gluconeogenesis are 3 reactions that can bypass these 3 irreversible reactions from glycolysis. And this is shown on this slide, and we'll see a similar slide in a little while, which shows that there are 3 so-called bypass reactions. The first bypass would bypass the last reaction of glycolysis, so don't get confused, okay? So gluconeogenesis actually goes from the bottom up, and glycolysis would go from top to the bottom here. If you look here, you can see glucose, glucose 6-phosphate, and so on. So if we start at the first reaction of glycolysis, because it is more familiar to you at this point, it would be the hexokinase reaction or glucokinase reaction where glucose is phosphorylated to glucose 6-phosphate. And this reaction is irreversible under physiological conditions and has to be bypassed. And there's a reaction that does this. Okay. Same is true for the phosphofructokinase reaction in glycolysis, which will have to be bypassed with another reaction. And then the pyruvate kinase reaction, the 10th step in glycolysis, is also irreversible in glycolysis, okay, and has to be bypassed. And we can already see here from this larger bracket and more reactions here, this is a little bit more complex and actually involves at least 2 reactions. And we'll start with this because this is from the point of gluconeogenesis, the first reaction, and it's also shown here as the first bypass reaction. And the other 7 steps, okay, which in glycolysis were already irreversible, are shared with gluconeogenesis and are utilized in gluconeogenesis. So the very same enzymes that in glycolysis catalyze these 7 reversible reactions are also utilized in gluconeogenesis, in liver and kidney. Okay. So this is our first bypass reaction, and as I said, we start with pyruvate as a starting material here. And pyruvate, as we've already learned, can be converted in the mitochondrial matrix into oxaloacetate. Do you remember in which context we discussed this reaction before? filling up of the citric acid cycle. So the term you can use there is it's an anaplerotic reaction. Anaplerotic just means filling up, so it's the same thing. So we talked about this reaction because we learned that oxaloacetate can be utilized as a starting material for the biosynthesis of some other things, okay? And we have to fill up the citric acid cycle again, because otherwise we can't continue going through the cycle for energy production. So this reaction is one of the reactions that is important to fill up the citric acid cycle and produce oxaloacetate again. And it's a carboxylation of pyruvate that requires energy and requires the involvement of a cofactor. Do you remember the cofactor that we discussed in this context? You should know that. Biotin, okay? It's a carboxylation reaction that requires biotin, and we've seen this slide or a similar slide before that shows actually this carboxylation of pyruvate. So energy is required in the form of ATP, is converted to ADP. We activate this bicarbonate to facilitate the attack of one of the nitrogens of our urido group of biotin. Remember the structure here, to carboxylate biotin. And from here we have a transfer of this carboxyl group to our 3-carbon compound, here the pyruvate, okay, shown here as carb anion, make it a better nucleophile to attack this partially positive carbon, here transfer this carboxyl group here to make it a 4-carbon alpha keto acid, which is oxaloacetate, and we generate our cofactor in this pyruvate carboxylase, okay. So this happens in the mitochondrial matrix, but the next step that actually leads to the conversion of oxaloacetate to phosphoenol pyruvate, remember phosphoenol pyruvate from glycolysis, super high energy compound, occurs in the cytosol. And we've also learned that oxaloacetate cannot be transferred across the inner mitochondrial membrane. There is no oxaloacetate transporter. But we learned that it can be indirectly transported in the form of malate. In what context did we learn about this? Try to stay on top of things. That's something we discussed week before spring break. Conversion of oxaloacetate to malate or vice versa. That's something you absolutely should know. At least 2 incidents where we talked about this.
It's like the way to transport NADH using the respiratory.
Exactly. It's involved in the thinking. It's involved in the malate aspartate shuttle that is utilized to transfer indirectly NADH that is produced in the cytosol across the inner mitochondrial membrane, so that it's then produced as NADH in the mitochondrial matrix and can enter the electron transport chain via complex 1. Okay, so this is one of the 2 shuttle systems that we discussed for NADH transport, which is a real transport, as you know, across the inner mitochondrial membrane. But what you should remember also for sure is the conversion of malate into oxaloacetate in the citric acid cycle. Okay. So, but here we actually utilize this to convert oxaloacetate in the mitochondria first into malate, and malate can then be transported across the inner mitochondrial membrane, utilizing the same transporter that we discussed in the context of the malate aspartate shuttle system. Okay, and in the cytosol, we can have the reverse reaction, so that we produce oxaloacetate in the cytosol, and this oxaloacetate is then converted into phosphoenol pyruvate by an enzyme that is here abbreviated PEPCK, okay, PEPCK, which stands for phosphoenol pyruvate carboxykinase. Okay, so all these names are tongue twisters, get used to it. Phosphoenol pyruvate carboxykinase. And what this enzyme does is shown on the next slide, it actually converts oxaloacetate, our 1, 2, 3, 4 carbon alpha carboxy acid here, which is also it's alpha keto acid, excuse me, into our 3 carbon super high energy compound phosphenol pyruvate. Now, we shouldn't be surprised that this is an energy requiring conversion, because we have a high energy compound that we produce here, so it actually requires GTP. But what I want you to see also is that this decarboxylation is decarboxylation of a beta keto acid again. Okay, so if you look at this carboxyl group here on this side, with regard to this end of the molecule, this ketone is in the beta position. This would be the alpha carbon, this would be the beta carbon. I told you that beta keto acids are not particularly stable, which facilitates here the decarboxylation. And then we have transfer of a phosphate here to this oxygen to form this enol here in our phosphenol pyruvate. Okay, so this is our first bypass reaction, which actually requires these 2 steps. You'll see that it's slightly different when lactate is actually the precursor. Okay, so again, here we have this kind of overview that we saw previously, and some numbers attached. Don't get confused by these numbers here, because I think here they don't really have the right sign, negative or positive, so necessarily it doesn't really matter. But I showed this slide just to remind you that after we have produced phosphenol pyruvate in our first bypass reaction, we can utilize the enzymes that the liver, let's focus on the liver here, okay, utilized under different circumstances in glycolysis, okay, but now it's about glucose synthesis, up to the point where we reach fructose 1,6-bisphosphate, okay, and the reaction again of glycolysis was catalyzed by phosphofructokinase 1. It's an irreversible reaction, glycolysis, so we have to bypass this reaction. The phosphofructokinase reaction was, remember that, phosphorylation of fructose 6-phosphate to fructose 1,6-bisphosphate. So this was a classical kinase reaction. The opposing enzymes to kinases are what?
Phosphatase.
Phosphatase. Okay, so why not use the appropriate phosphatase? Okay, to cleave off the phosphate here from the carbon number 1 in fructose 1,6-bisphosphate to produce fructose 6-phosphate. And we do this by utilizing fructose bisphosphatase. Strictly speaking, we should call this fructose bisphosphatase 1, because there's also number 2. And also here, this phosphofructokinase, which is part of glycolysis, should have this 1 to distinguish it from 2. Okay, so never mind, we use an appropriate phosphatase. It's called bisphosphatase because we have 2 phosphates on our substrate. Okay, don't get confused by this. To convert fructose 1,6-bisphosphate to fructose 6-phosphate. Then we can utilize our phosphohexose isomerase reaction. Here the enzyme is called phosphoglucose isomerase reaction. It's the same enzyme, to convert fructose 6-phosphate to glucose 6-phosphate. Remember this mechanism that I discussed that goes through this cis-ene diolate, okay? It produces in the reverse reaction glucose 6-phosphate and not mannose 6-phosphate, okay, because it's a stereoselective reaction. And then we have to convert glucose 6-phosphate to glucose. Again, in glycolysis, this was catalyzed by hexokinase, glucokinase in the liver. It was an irreversible reaction in glycolysis, so we have to bypass it. It was a kinase reaction, so why not use a phosphatase? Okay? And we have the glucose 6-phosphatase actually that we can utilize for that. Okay? So here are 3 bypass reactions. I'm not going to talk about the steps that we already discussed in the context of glycolysis because they are the same reactions. Now, all the enzymes besides what I discussed for the first bypass reaction, what I'm going to talk about also in a moment for the first bypass reaction when lactate is the starting material. All the other reactions up to this point actually occur in the cytosol. Okay, remember glycolysis occurs in the cytosol. If we share the enzymes, okay, we do this in the cytosol. But what is interesting is that this last step in gluconeogenesis, catalyzed by glucose-6-phosphatase, does not occur really in the cytosol, but this enzyme is found in the endoplasmic reticulum. Okay, and this is shown on this slide where we have our glucose-6-phosphatase here embedded in the membrane of the endoplasmic reticulum, and the reaction actually that cleaves glucose-6-phosphate to glucose then is catalyzed by a catalytic domain that is facing the lumen, so the interior part of the endoplasmic reticulum. So the glucose-6-phosphate is actually transported into the endoplasmic reticulum lumen, and then we have this hydrolysis reaction which cleaves off the phosphate from glucose-6-phosphate and produces glucose, and then those phosphate and glucose can be transported out to the to the cytosol again with appropriate transporters. So this is actually quite interesting, I think. Good. So if lactate is the precursor for gluconeogenesis, the reactions are a little bit different. Okay, and I guess this is primarily based on some empirical observations also. I have a hard time really understanding this, but it seems to be the fact that this actually happens. But when lactate accumulates, then lactate can in the cytosol be converted to pyruvate with lactate dehydrogenase. We actually produce NADH here. Pyruvate can be transported with pyruvate translocase into the mitochondrial matrix, can be carboxylated as we heard to oxaloacetate in the mitochondrial matrix. And then there is a mitochondrial isozyme of phosphoenolpyruvate carboxykinase, which in the mitochondrial matrix can convert oxaloacetate into phosphoenolpyruvate, which can be transported out into the cytosol. So this is a little bit different, and it has been found that if one knocks out in mice the mitochondrial isozyme, then gluconeogenesis utilizing lactate and some other precursors is actually impaired. So this really seems to happen, because I always, when I prepare this part of the class, I always ask myself, okay, why would we go this other route really? But okay, it seems to happen. Okay, don't really have a good explanation for it. Okay, but in the textbook, I think it's just stated matter of fact. Okay, this happens when lactate is the precursor. Okay, it does, but why? If we look at the net reaction of gluconeogenesis, we can see a couple of things. So first of all, we produce a 6-carbon sugar utilizing, as we discussed it here at least, 2 3-carbon compounds, namely 2 molecules of pyruvate. Okay. What is quite obvious here is that this requires quite a bit of energy. So we actually utilize 4 ATP molecules and 2 GTP molecules, meaning we utilize 6 ATP equivalents, and on top of this, we also utilize 2 molecules of NADH. Okay, so the glycerol-3-phosphate dehydrogenase reaction utilizes NADH then in the 6th step of glycolysis in the reverse, okay, gluconeogenesis, just to produce glucose. So this is a lot of energy. And this also, whenever you see consumption of energy, or especially a lot of energy, it implies that this production here, in this case of glucose, must be of extreme importance, because otherwise nature wouldn't have gone this far. Okay, it just wants to conserve energy. Here we expend actually 6 ATP equivalents in 2 molecules of NADH. Okay, so since we want to avoid that glycolysis and gluconeogenesis occur at the same time in the liver, or kidney for that matter, both of these opposing pathways have to be regulated. And we see from this slide that they are regulated in an opposing reciprocal manner. Excuse me. So if we include also the pyruvate dehydrogenase complex reaction which utilizes pyruvate to produce acetyl-CoA, which is channeled to the citric acid cycle, we see that, you may remember that this complex is actually inhibited by acetyl-CoA. We talked about this when we talked about the regulation of the pyruvate dehydrogenase complex and the citric acid cycle. You may also remember that pyruvate kinase can be inhibited by acetyl-CoA, so this is all utilization of glucose. Okay. Now, pyruvate carboxylase, which actually produces or is part of the gluconeogenic pathway, is actually allosterically activated. Okay, so this is opposing to what happens if we consume glucose. Similarly, in our discussion of the regulation of glycolysis, we learned that phosphofructokinase 1 is activated by AMP, so if AMP accumulates, signals an energy insufficient state. On the other hand, the fructose bisphosphatase 1 is allosterically inhibited by AMP. Okay. What is of great importance also is here the regulation of phosphofructokinase 1 and the corresponding fructose bisphosphatase 1, because they are also inhibited in a reciprocal manner. So we learned that phosphofructokinase 1 is activated by fructose 2,6-bisphosphate. Remember, fructose 2,6-bisphosphate is the most potent activator of phosphofructokinase 1, which is the most important regulatory enzyme in glycolysis. So phosphofructokinase 1 is activated by this molecule, fructose 2,6-bisphosphate. On the other hand, the opposing enzyme, fructose bisphosphatase 1, which cleaves off this one phosphate from carbon number 1, fructose 1,6-bisphosphate, is inhibited by the same molecule. Okay. We already talked about the production and degradation of this allosteric modulator, fructose 2,6-bisphosphate. It is produced from fructose 6-phosphate in a kinase reaction, catalyzed by phosphofructokinase 2, remember that? And it can be degraded again to fructose 6-phosphate by cleaving off the phosphate on carbon number 2 with the fructose bisphosphatase 1. And I told you that both of these enzymatic activities are located in the same protein, this tandem protein. Do you remember that? And whether or not the kinase activity is on or the phosphatase activity is on depended on the state of phosphorylation. Hope you remember all that, okay? Because now we are revisiting this and we include our discussion of the regulation of the fructose bisphosphatase 1. Okay. So I told you that when blood glucose concentrations go down, glucagon is secreted by the pancreas. You may remember that glucagon then binds to target tissues, to membrane-bound receptors, glucagon receptors, also in the liver, okay, and then we have signal transduction cascade, which via adenylyl cyclase may lead to an increase in the intracellular concentration of cyclic AMP. We talked about this. And the cyclic AMP actually activates cAMP-dependent protein kinase, or protein kinase A, which can phosphorylate target molecules. I hope you remember that. Okay, this is shown here. So cAMP-dependent protein kinase is activated when glucagon is secreted, meaning when blood glucose concentration goes down, and it phosphorylates our tandem enzyme. Okay, this phosphofructokinase 2/fructose bisphosphatase 2. In the phosphorylated state, we learned that phosphofructokinase 2 is inactive, but now we also see that the fructose bisphosphatase 2 activity is active, which leads to a removal of fructose 2,6-bisphosphate, because the phosphatase activity will cleave off this phosphate from carbon number 2. We have less of this compound and less activation of phosphofructokinase 1, and with this we have effectively an inhibition of glycolysis. Okay, so what this means is that when our body realizes that blood glucose concentrations go down, it will slow down glycolysis in the liver. Okay? On the other hand, since we have less of an inhibition of fructose bisphosphatase 1, if the concentration of this allosteric modulator goes down, we have a stimulation of gluconeogenesis. Okay? So as we then cleave off, hydrolyze off this phosphate, we have actually the phosphofructokinase 2 activity on and the fructose bisphosphatase 2 activity off. We increase the concentration of our allosteric modulator, fructose 2,6-bisphosphate. We stimulate glycolysis and we inhibit gluconeogenesis. Okay, so one way that I personally remember all of this, okay, what effect does phosphorylation have is by just thinking that if blood glucose concentrations go down, glucagon is secreted. Okay, and then I remember that if glucagon is secreted, our CAMP levels go up and I activate this protein kinase A. So glucose levels down in our blood means I have to produce glucose in gluconeogenesis in the liver. So everything else I can put together from just this simple understanding. And then